Hello everybody, this is Rudra Pradhan here. Welcome to Engineering Econometrics, that too on time series modeling. We will continue with volatility modeling. In the last lectures, we have highlighted a lot about the volatility modeling, and that too basically the structure of nonlinear time series modeling. We have slightly highlighted some of the nonlinearity issues, and then we have discussed basics of like Ramsey's test, then BDS test, then the artificial neural networks, and now we will come down to the kind of structure, the most important models which actually use in the real life scenario, that to solve some of the volatility issues in engineering problems. Typically, the structure is like this. Let us start with basics about the volatility, historical, which called as historical volatility. The simplest method for volatility is the historical estimate. Historical volatility simply involves reporting the standard deviations or the kind of variance of a variable. Basically, the use of historical data, that means variables information recorded historically over the time. The volatility forecast we do with the help of past data and do for the kind of future requirement. Evidence suggests that the use of volatility predicted from more specific sophisticated time series models will lead to more accurate forecasts and option valuations. That is in a kind of financial markets. Historical volatility is still useful as a benchmark for comparing the forecastability of more complex time periods. Okay, so that means this is the issue about the historical volatility. So now the question is how will you go about it and what kind of things you are supposed to bring, so that we can address this problem more effectively, okay, and as per the requirement of some of the engineering problems and the kind of decision making process. Let us start with your simple models. Means when we will discuss about the volatility modeling, so one of the biggest component is the error term, which is actually derived through the actual structure and the estimated structure. And when we have the estimated structure, that can be started with one independent variable or many independent variables. That means whether it is a bivariate structure or multivariate structure, we have no issue. We means every time there is a dependent variable and series of independent variables, starting with at least one or many. Then ultimately end of the day we have the game between y and y hat, which brings the error terms, that is the difference between the y actual, that is the dependent variable actual, and y estimated, that is the estimated dependent variable. Now, whether the dependent variable is a function of one independent variables or many independent variables, that is not the big deal. Of course, as per the problem description is concerned, the kind of requirement is concerned, we have to put one after another variables in the system, that too in the form of every time dependent variables, because this kind of model is a kind of one way structure, where dependent variable is a kind of single, and then other variables will be entered to the system as a independent variable. That is what the entry point, and that is what the kind of logic, and that is what the kind of structure about the arch and gauge cluster. So now a basic structure is, let us start with simple model here. We have a model here where y is the dependent variables, and then we have a series of independent variables, 3 independent variables we have taken, x2, x3, x4, and then we assume that the error terms which will derive by this estimation process by using some time series data. So, which we have mean error 0 and then variance sigma square u constant, and that is the requirement of ordinary least square mechanism. And if that is the case and that happens in any problem, in any context, in any situation, that is what the declaration is called as a homoscedasticity, which we have already gone through it. However, if the variance of these error terms are not actually coincide, or it means they are not same and not constant, that is what the term called as heteroscedasticity, and that is the beginning of this volatility modeling, that to arch cluster and gauge clusters. So, that means the entry or the understanding of arch cluster and gauge clusters, or the requirement of the arch cluster or gauge cluster is the error term and the error variance typically. So, once you find out the estimated models and then you derive the error terms and error variance, then the game will start here in another mode, and then try to check the kind of rules, regulation and the kind of requirement about the prediction and forecasting. So, that means we would simply say that standard error estimate could be wrong, that is what the kind of so is the variance of the errors like to be constant over time. So, that is what the questions will be usually expecting in the process of this modeling. So, now basically this is the deal, and then we start with after knowing the particular basic structure about the functionality, model estimation, obtaining error terms, error variance, then we will move to the kind of clustering called as volatility clustering, that to volatility modeling, starting with the arch modeling first and then gauge modeling the later. In the arch modeling, it is the kind of game where error variance as a function of error terms, and the gauge modeling, it is little bit more comprehensive, much attractive and much broader by including the log of these error variance in addition to error terms, square of the error terms. So, let us see how is these models. Let us start with the first arch and then move into the gauge model. That is what the starting point of arch models, that is technically called as autoregressive conditional heteroscedasticity. So, we start with the usual structure about the estimation process, whether it is a bivariate structures and the kind of trivariate structures or the kind of multiple structure. Ultimately, we need a error term u, which we call as ut, and then the error variance sigma square u, which sigma square, which is called as sigma square ut, and that is what the actually error variance here sigma square, and which is actually calculated by this process. And then the conditionality is that as per the OLS requirement, error term should converge to mean, means mean of this error term converge to 0 and variance of this error term should be converged to 1. That is what the normally distributed with the 0 mean and unit variance, that is what the requirement. Sometimes it may not be the case when the error variance is not unitary. So, that brings the kind of variations. That means, instead of saying sigma square u, it becomes now sigma square ui, that creates a kind of functions. If it is a constant, then it will like single figures. Now, if it is not constant, then it will be more than the particular single figures. That is how they brings the functionality. So, now how is this game actually, the arch clusters? The arch cluster simply connecting to the error variance to the square of the error terms, and that to log of the error terms like this. So, that means technically the game will be like this. we have yt, then yt minus 1 and yt minus 2 and so on like this. Either the prediction will be like this, yt with you as a function of yt minus 1 and something like that, or yt as a function of another variable say x and something like that, and then we have estimated y, and the difference between these two will give you the error component. That is the big deal in a big requirement of the first instance. And after knowing the error terms, okay, now the deal will be in this term ut minus 1, ut minus 2 and so on. In another way, it can be ut squares, ut square t minus 1, ut minus 2 square. So, that means it is a squaring all these error terms, log of these error terms. The advantage is that all these variables have now kind of positive in structure, and which may have some kind of better indication compared to the the actual kind of error behaviors. So, now the first models which we call as arch models, starting with the general form is like 1. This is arch 1, where simply error variance is connected with the square of the first log error variables. That is what called as u square t minus 1. So, that is what here is. We are here u square t, and we like to connect with u square t minus 1, t minus 2 and so on. Technically, since they are time series data and the error component by default will follow the time series, as a result every time there is high chance the log of variable will be well connected to the previous log variables. So, that means technically u t minus 2 depends ut minus 1 and something like that. So, ut technically function of ut minus 1, ut minus 2, that means every current variables will be predicted through the past that is the fact, that is the time series structure altogether. So, it has well connection with just behind, that is what the historical data is all about. So, when we will call as arch 1, then simply we are connecting with first square log error term, that is what is called as u square t minus 1. That means, this is what the kind of structure, and we like to just check the coefficient of these terms would be statistically significant. If that is the case, then it will give value about this model, and then we will check the reliability, validity, and then use this model for the predictions in comparison with the simple linear estimations, right. That is what the kind of game, and that is how it is very simple. So, you go to the we will go to the Excel sheet, and the process which you have actually to have these variables. For instance, let us say this is a data, and we like to first let us say this is a sales data, and that is in a time series recording, let us say annually for last 23 years, and then the advertising expenses in this organization over the last 23 years. That means, it is a time series structures, and we need to predict actually sales by advertising, and that to check the check the kind of forecasting through volatility modeling. So, the first instance of this process of arch and gauge cluster use this data and predict the either two way you can do. So, I call it sales is yt, okay, and then advertising we call is xt. So, there are two way you can enter to this process, yt as a function of yt minus 1 or yt minus 2 and so on. How many logs we will use, that depends upon through AIC statistic and SIC statistic, which you have already discussed, and or else you can just connect with y and x and then find out the error terms, and that error term can be used as a benchmark for arch modeling and gauge modeling. For instance, let us say these are the two variables, and then we go to the data analysis. Of course, there are time series technique, EViews, microfit, all these things, but since it is not here. So, what will we do? Will do this through Excel, but will do some kind of extra processing. So, let us have the regression first, and then this is what the dependent variable requirement, and then the independent variables, that is what the independent variable requirement, okay, and then run the models. Now, we have 38.45 minus 0.02, okay. So, that means we will go to this structures, then we will have actually this is y kf, okay, and that y t, that y trans at the time period t is equal to 38.446, okay, 38.46, that is okay, equal to 38.46, okay, and then here it is a kind of 0.03, okay, 38.46 and 0.03, okay, this is plus 0.03, okay, then multiplied by the kind of independent variables, okay. If you connect with the simply log variables, then y t minus can be regress, and then the estimated line can be drawn. So, this is what the predicted informations, okay. All right. Now, we will have a error component, that is the u, okay, which is actually the difference between the kind of y actual minus the y estimated, that is what the error term, okay. Now, we will have like, okay, just okay, we can scroll it this ones, then it will be generated, that is what the u t generated, okay. So, what will you call square u error terms, okay, which is just equal to actually this this multiplied by again this, all right. So, this will be actually the error term square, right. This is what the square if we call it u t, and then this will be actually square of the u t, right. That is what the dependent variables, and then we create actually log of square u t. So, that means s q r u t minus 1. So, okay. So, this is the first log, and likewise you can go about s q r u t minus 2, that is what the kind of I will just a little bit enlarge the view, that is square u 2, okay. So, now what you can do, you can just create this one. So, this is the square u t which you have already created. Now, we need to create actually the log of these variables. So, you just go and then copy, that is one, okay. This is the other one. Likewise, you can create here n number of variables, that is very easy to do that, okay. That is very easy to do that, it is very easy, okay. All right. So, you have actually lots and lots of variables in the kind of case, and then so we like to connect actually this with this again, that means technically now this is the data set, and technically since we have created lots of log, if you go up to all logs, then this much we start this sampling from here only, okay. So, this much of sample will be finally added into the process. Now, the first arch model will be this with square of these terms, right. That is what the kind of So, now again you go to the regressions, and then this will be the dependent variable and these will be the independent variable, and do the estimation. That is what we are discussing here all about now, okay. So, when you call at first arch 1, so that means we are connecting with first square of the log term, that is u square t minus 1, right. And when it go for arch 2, then alpha 1 is square t minus 1, then alpha 2 is square t minus 2. So, two different estimates you will find, and then it can be also generalized. It can be also generalized. So, that means taking the clue from the previous discussions you see here. So, this is what the first and starting, and then we will have the error terms, then the first error variance with the first error term, that is arch 1, and then if it is actually say called arch 1, and then this is actually called as a arch P or Q. Okay. So, it is a Q here. So, you can call it Q, right. So, that means it will. So, that means technically we can have the model up like this, we can model have like this, or we can model have like this. Now, the question is what is the correct one. So, that is for that you can go again AIC, using the AIC statistic, SIC statistic, and final prediction errors, something like that. Then you fix the log length first. So, since it is a time series models and to that too in the log modeling. So, fixing the optimum log length is more important first. After fixing this one, then you will go for other kind of requirements and the kind of estimation, then the kind of testing, the reliability. So, everything will come one by one. So, but this is very important, how to fix the optimum log, and that is what the one of the biggest challenge in the time series modeling, and that to this type of models. So, now instead of calling variance sigma square, the literature it is usually called HT. So, so that means technically, so HT is a sigma square error variance, which is actually connected with these terms. That is what the this is what actually generalized format of autoregressive conditional error scarcity, and we can have little bit extensions by putting the log of this error variance into the system, then extend this model to the arch clustering and something like that, but it is the similar structure here, how you have to behave with respect to the kind of situation and the kind of requirement. So, that is the form of arch modeling. So, that means technically it is actually a second step process where the original variables are not here. So, means technically we start with y and x, but ultimately the models are different variables as error variance, then square of the error terms, and log of the error variance. So, these are all items which are derived from the original variables y and x, but ultimately the final prediction with respect to their error terms, which is the difference between the actual and the estimated. That is the beauty, and that is what the difference different kind of look and status compared to the kind of discussion which we have earlier. In the earlier case, some of the cases we use actually models every time dependent variable will be targeted, and error term can be used as a instrument to check the validate the model, but final prediction is with respect to the dependent variables, original dependent variables y t, and then the independent variable and through the error terms. But here to predict this dependent variable through this independent variable, we use actually error terms instead of the actual y and the actual x. That is what the big deal, and here is the general structure of this kind of say the kind of say the arch modeling, and we start with this particular concept, and then finally this is what the model about the arch. So, that means there are two different ways of expressing exactly the similar kind of structure. The first form is easier to understand, while the second form is required for simulating from arch models only. Okay. That is what the actually sigma 2 equal to square root of this, because it is simply sigma square equal to alpha 0 plus alpha square u t minus 1, and that too for arch 1, or just keeping sigma 2 by default the other side will be square root, and then we can do this kind of estimation. So, that is the big deal actually, and we like to actually understand the structure Now, after building the kind, this is the first step, and then bring the arch, means let us say actually 3 step process altogether. In the stage 1, you have the actual problem set up with a clear cut identification of dependent variable and independent variable, and then we have estimated dependent variable, that is what technically called as a y cap, and then in the second step you need to find out the error term, which is the difference between the actual dependent variable y t and the estimated dependent variable y k f, and then we will get the error terms. After getting the error terms, then you will get error variance, and then connect with square of these error terms. Okay. And after getting the error term and the log of these error terms, then we have to set again the form of model. We say the form of set the form of the particular model, and again this model will be rerun and to get the estimated structure. That means technically we like to know these parameters values. Okay. And again, so that means it is completely new setup altogether, where the square of these error terms, right, that is what here actually, and connecting with all these log error terms, that is what the big deal. And then we connect with again the data structure, the kind of regressions, and then finally we can get the estimated values of all these parameters, starting with this ones, this one, this one. So, all these parameters actually. So, we will find here, and then finally we get actually R square as usual. Now, we need to first test the models by using actually T R square, and that too through chi-square test, justifying that the R square is actually supporting the kind of requirement. Okay, that's very similar process altogether. Only thing is the formulation of the first step and the second step, that is the basic understanding, and then rest of the things as usual actually structure. You see here what I have told. So, the null hypothesis to test that all these parameters to be statistically significant along with R square, and for that we use chi-square, and for this parameters we can use t test, and then we can actually justify the kind of requirement. If the values of the test statistic is greater than the critical value from the chi-square distribution, then we can reject the null hypothesis. That is the usual procedure again, and note that the arch test is also sometimes applied directly to return instead of the residual from the single one. That is the another kind of. So, now couple of questions. First thing, how to decide the q, that is the number of logs, and the required q value of q might be very large, or it should not be too small. Okay. Then this needs actually optimum one. If it is too large, then it may affect the process, that it may affect the degree of freedom, and then the whole process will be negatively affected. So, that is why the first requirement is how to fix the q, and for that I have already discussed and highlighted that we usually use IC statistic, SI statistic, FP statistics to decide the optimum log length, and then finally non-negativity constants might be violated. So, that means technically since we are squaring, so by default actually negativity will be not there. When we estimate an arch models, we require this alpha I should be greater than or equal to 0. Okay. So, since the variance cannot be negative, that's the big and big kind of information that you need to have before you apply this model for the kind of engineering forecasting and the kind of decision making requirement. And natural extension of ASCII model which gets around some of the problems, and that is actually connected with kind of say called as Gauch models, right. So, that means the this part is actually not so complicated. So, we starting with simple structure of estimation, then get the estimated model, error terms, then we get error variance, then square of these error terms, and as usual again second stage you can just connect with a simple regression by a error term with square of these log error terms, and that's as usual as again regression. Then through that output we have to predict the kind of engineering output and engineering requirement, and then come with a kind of decision making process. Similar kind of model, but it is the 2-3 stage extra things we are supposed to do to bring the scenario that which can have a better kind of forecastings as per the particular engineering requirement and the kind of decision making requirement. This will stop here, and in the next class we will discuss the counterpart, that the GACH models. Thank you very much. Have a nice day.